Welcome to my YouTube channel. This is Dr.Sengolrajan, Associate Professor in the Department of Electronics Engineering from Tamil Nadu College of Engineering and Technology, Kottayam, Tiruchirappalli. Now, in this video, I am going to discuss about strain gauge. Strain gauge from sensors and transducers. How Let me discuss first how this strain gauge has been working. Strain gauge has been working based upon piezoresistive effect. What is piezoresistive effect? When you take a metal conductor, when this metal conductor is stretched, when this metal conductor is stretched or or compressed. Stretched means you are elongating. Compressed means it is decompressing. So when a metal conductor is stretched or or compressed, its resistance changes on account on the fact that both the length and the diameter of the conductor changes. Both the length and diameter of the conductor changes. Also, there is a change in the value of resistivity. Also, there is a change in the value of resistivity of the conductor when it is strained, and this property is called piezoresistive effect. That means when you take a metal conductor and you apply a force, then based upon the force you are applying, the conductor may get stretched or compressed. Then when it gets stretched or compressed means elongated or comes back to its original position, its resistance will changes. The resistance changes, it depends upon the length as well as diameter of the conductor changes. So also there is a change in the value of resistivity of the conductor when it is strained, and this property is called the piezoresistive effect. Resistance strain gauges are also known as piezoresistive gauges. Coming to the uses of strain gauges, it is used for the measurement of strain and associated stress in experimental stress analysis. Many detectors and transducers uh, belongs to strain gauge. That is, one is a load cell, torque meters, diaphragm type pressure gauges, temperature sensors, accelerometers, and the flow meters employ strain gauge as a secondary transducers. Then coming to the theoretical discussions, if you see the diagrammatic setup, then here what force you are applying a tensile force. Then the length of the conductor is taken as a L. The diameter of the conductor is taken as a capital D. You are applying a force that is called a tensile force. Then this L will automatically get stretched and elongate to delta L. And the diameter D will get elongated from capital D minus delta D. Capital D minus delta D. In this diagram, it shows the changes in the dimensions of a strain gauge element when it is subjected to a tensile force. The change in the value of resistance by straining the gauge may be partly explained by the normal dimensional behavior of elastic property. If a strip of elastic material is subjected to tension, since the resistance of the gauge, a conductor is proportional to its length. Since the resistance of the gauge of a conductor is proportional to its length and inversely proportional to the area of cross section, the resistance of the gauge increases with positive strain. The change in the value of resistance of a strained conductor is more than that can be accounted for an increase in resistance due to dimensional changes. I repeat once again, the changes in the value resistance of strained conductor is more than that which can be accounted for an increase in the resistance due to dimensional changes. The extra change in the value of the resistance is conductor when strained. This property is known as piezoresistive effect. Then let us consider a strain gauge which is made up of a circular wire. Let us consider a strain gauge made up of a circular wire, not vice circular wire. The wire has two dimensions. One is the length equal to L, and the another one is nothing but a area is equal to A, and next one is nothing but a diameter D, which is being strained, which is being strained. The material of the wire has a resistivity rho. The material of the wire has a resistivity rho. The resistance of unstrained gauge. The resistance of unstrained gauge R equal to rho L by A. Rho L by A. Let a tensile stress S be applied to the wire. Let a tensile stress S be applied to a wire. This produces a positive strain. Positive strain. Let a delta L equal to change in length. Let delta L equal to change in length. Delta A equal to change in area. Delta D equal to change in diameter. And delta R equal to change in resistance. In order to find how delta R depends upon the material physical quantities, the expression for R is differentiated with respect to stress S. dr by ds. dr by ds is equal to rho by a into the dimensional changes, that is delta L by delta S minus rho L by A square, area of cross section, into rho L by rho S plus L by A into L by A into dou P dou rho by dou S. Dividing the equation 1 through the resistance R equal to rho L by A, then we may have 1 by R, 1 by R into dr by ds is equal to 1 by L. Through the equation we are dividing R equal to rho L by A, then automatically 1 by R into dr by ds is equal to 1 by L into rho L by rho S minus 1 by A into rho L by rho A by rho S plus 1 by rho into rho by rho S. It is evident from the second equation that per unit change in resistance, per unit change in resistance is equal to per unit change in length is equal to delta L by L. Per unit change in length equal to delta L by L. Per unit change in area equal to delta A by A. And per unit change in resistivity equal to delta rho by rho. Area A equal to pi by 4 d square, then therefore rho A by rho S is equal to rho A by rho S is equal to 2 into pi by 4 capital D into rho D by rho S. That is equation 3. Then 1 by dA by ds equal to 2 by 4 into capital D divided by 5 by 4 into d square into rho D by rho S, that is equal to, we will get 2 by D into rho D by rho S. The equation, third equation, we are rewriting is 1 by R dr by ds equal to 1 by L rho L by rho S minus 2 by D into rho D by rho S plus 1 by rho 1 by rho by rho S. Poisson's ratio. Here you are interlinking the Poisson ratio. Poisson ratio is represented as mu is equal to lateral strain divided by longitudinal strain. Here lateral strain is nothing but minus dou d by d divided by dou L by L. Here dou d by d equal to minus mu into dou L by L. Then coming back to 1 by R dr by ds equal to 1 by L dou L by dou S plus Q into 2 by L dou L by dou S plus 1 by rho dou by dou S. For small variations, the above relations can be written as delta R by R equal to delta L by L plus 2 mu into delta L by L plus delta rho by rho. The gauge factor is defined as the ratio of per unit change in resistance to per unit change in length. Here gauge factor GF equal to delta R by R delta L by L. Gauge factor delta R by R equal to gauge factor into delta L by L equal to gauge factor into epsilon, where epsilon is nothing but saying that is equal to delta L by L. gauge factor can be written as 1 plus 2 nu plus delta rho by rho divided by epsilon. That is equal to 1 plus 2 nu plus delta rho by rho divided by epsilon. Resistance change due to change of length. That is 1. Resistance change due to change in area, that is nothing but a 2 nu. Then delta rho by rho divided by nu, that is nothing but a resistance change due to piezoresistive effect. Here, in this manner, gauge factor equal to delta R by R divided by delta L by L is equal to 1 plus mu h plus delta rho by rho divided by delta L by L. 1 microstrain is equal to 1 micrometer per meter. That if the change in the value of resistance of a material strain is neglected, the gauge factor is GF equal to 1 plus 2 mu. Valid only resistivity effect, that is change in resistance due to strain, is almost negligible. The Poisson's ratio for all the metals is between 0 and 0.5. This gives a gauge factor approximately 2. The common value for Poisson's ratio for Y is 0.3. This gives a value of 1.6 for Y-only strain gauges. The various types of strain gauges are unbonded metal strain gauges, bonded metal strain gauges, bonded metal foil strain gauges, vacuum deposited thin metal film strain gauges, spotter deposited thin metal strain gauges, bonded semiconductor strain gauges, diffused metal strain gauges. Thus, the strain gauges is working with respect to piezoresistive effective principle. Then we are going to apply a tensile force to the material. Then based upon the tensile force activations, we can be able to calculate how much stress applied for the how many, what is the strain that is being calculated. Meet you in the next video.